Today we have two guest speakers, Andre and Luc from Mozilla. So, if you're asking why is Mozilla on this talk, Mozilla, they've been a very important partner in getting Unity to work on WebGL. They were, in the first place, they were the ones to convince us that this would be possible at all, because we didn't quite believe that a few years ago. But also they have been driving this technology quite strongly and have been helping us a lot with all our development on this. So we will start with Andre from Mozilla giving you some stats on the audience of web gamers. Then I will talk about the current state of the WebGL export in Unity together with Marco. We are both engineers on the WebGL team. And finally, Luc from Mozilla will give you a bit of an outlook of the ecosystem of browser technologies driving this. So, Andre.
Thank you. Hi, everyone. Good. My name is Andre Vrignaud, and I am the games platform strategist for Mozilla. I'm here to talk to you about a survey that we did of our Firefox users to understand better the web audience and share some data. I think this is actually the first time we've done something along these lines, so hopefully you'll find it useful. Just to back up real fast, if you need to contact us, that's my obnoxious email address. You can also just remember games@Mozilla, and that gets to us too. Put a .com on the end, works better. So why does Firefox care about games? It's pretty simple. Our mission is to promote openness, innovation, and opportunity on the web. Games have been an amazing technology catalyst across all sorts of industries. It pushes us on performance. We find a lot of opportunities to go invest in the games web stack, which ends up having benefits down the entire web ecosystem. So we've been investing in it and working with partners like Unity for the last few years. Overall, games are very important to us, and we wanted to kind of understand the audience a bit better. And so this is where we kind of went into a survey. So let me talk a little bit about the methodology. We have a tool called Heartbeat. It's a user sentiment survey tool. It is a blind survey. So when we fire off Heartbeat, we send up a little box that appears that basically shows users, hey, how are you feeling about Firefox today? And there's a sad face and a happy face. And users tell us that, and that gives us a sense of how things are working. Only after they've done that are they prompted with a survey. And that's the first time that a user will actually find out whether or not they're going to be taking a survey on one topic or another. At that point, we had less than 3% people drop. So we had a lot of people go through doing what was actually a pretty long survey. Our user research guys weren't terribly happy with me for all the questions we wanted to ask. We got 2,200 eligible results. Statistically speaking, 1,000 is kind of the break-even point after which the stat guys start saying it doesn't matter too much. So it was really nice for us to get all this extra data. You'll notice that there's a bit of a bias here toward male, and we also have a bit of a bias toward the most active Firefox users. Just want to be clear about that. The reason we have the most active Firefox users is because the Heartbeat survey comes up about 5 minutes into a survey, into a session, and what you'll end up finding is that there's people who might use the browser once a month or once a week who simply might not appear there. So these are going to be some of the more active users, more dedicated users. We also have found that generally, when you look at survey results for the game industry, they're roughly 50-50 men, female. Here, it's about 66% male. That's just a well-known bias that we have in our Heartbeat results. For some reason, men seem to like surveys. I have no idea why. All of the data following is going to be for the gamers who self-identify, for the users who self-identify themselves as gamers. I'm also going to be blazing through. There's a lot of data, so bear with me. A couple of major themes. One, web users are gamers. Not a terrible surprise, but we found that consistently. The audience is a very familiar one to you as a developer. You're not going to have any huge surprises. Browser games are very popular, and we're going to highlight a few areas where some core opportunities exist. And no surprise again, web gamers are very social and connected. So let's look at the audience. Again, remember, this is the Firefox users that have self-identified as gamers. What we found is a very similar 24 to 34-year-old peak that you've seen many times as a traditional audience, gaming audience. Men and women are equally likely to be gamers. Non-gamers also skew older. You see the curve there on the bottom with the orange. Top gaming platforms. One of the interesting ones that we found was 77% of the Firefox audience self-identified as gamers. Pretty high number. Now, I want to be clear, this is the Firefox audience, and we can't generalize it and say this is absolutely true of the web at large, but it's a reasonable proxy. It's an area we're going to go explore some more data, some more surveys in the future. PC gaming is incredibly popular with over 70% of our users. Context, again, this was a survey fired off to Firefox users on a desktop PC, so you might expect a pretty high percentage there. The browser, this is kind of interesting. The Firefox browser is a games platform. It's just nipping on the heels of the smartphone and consoles, which was pretty intriguing to us. And you'll also see in the very top bar that PC gaming has more highest usage gamers than other platforms. Overall gamer genre interest. So this is a view merged of the PC or the download market, the browser users, and mobile genres all merged together. Pretty standard. If you've seen surveys of genres, this is a pretty common curve. Role-playing puzzlers and first-person shooters came up very high. Other was basically people just not sure, Minecraft or solitaire, brain training games are some of the responses we got there. So next time we do a survey, we're going to try to add a couple of those categories and see if we can reduce that. So let's take a look a little bit at what the in this case, the web browser gamers actually prefer. You'll notice that when you compare the PC on the top and the orange, which is the web browser gamers on the bottom, browser gamers slightly prefer simulations, social games, and word game titles. This might be kind of a symptom of the prevalence of Facebook and web browsing and web games today. PC users, not a terrible surprise, prefer RPGs, shooters, and strategy games. However, it also kind of highlights a potential opportunity for underserved users on the browser. Now that the web game technology stack, WebGL, as Unity calls it, is beginning to solidify, there may be an opportunity to target that audience. How much do they play? Firefox browser gamers have fewer gaming hours than PCs and consoles, but they have more total hours per active user than smartphones. It's pretty interesting when you think about the prevalence of smartphones and smartphone gaming. Also interesting is the PC dominance in the greater than 10-hour bucket, which also hints at a strong core web game opportunity. How often do they play? 28% of browser gamers play multiple times a day, compared to 44% of PC gamers, 33% of mobile gamers. And now a set of slides on their social gaming, or their social network participation. No huge surprise, Facebook is by far the most popular. We did find very interesting that console networks, Twitch, were approaching the popularity of Instagram with gamers. About 19% of users don't actively use social networks. So how many social networks are they on? Another interesting finding was if you look at the first 4 bars here, pretty consistent. Basically, 18 to 44-year-old gamers average 1.7 social networks. Social network usage drops off pretty quickly after 45 years of age. Sharing. 34% of these gamers share game-related content. Of the ones that share, screenshots are the most common, videos being the second, and then in-game content following. What do? When they interact, they tend to interact most over real-time games and chat. Kind of makes some sense. I thought it was a bit interesting that the turn-based games were significantly lower. That may be an opportunity to look at turn-based games as an underserved area. 42% of players didn't play with others at all. That was also kind of interesting when you think, it would be interesting to see what that stat is when you look at something like Xbox Live or PSN, where there's a robust backend for connecting people. That's not as consistent on the browser/PC side of things, and that may be one of the reasons for that. Who do they play against? 20% of players play equally against real-world people they know, people they don't know, real people they don't know online, or both. Kind of interesting that stats seem to be pretty consistent across the board, and online play is inversely correlated with age, dropping as you get older. So to wrap up, some takeaways. Again, 77% of the Firefox audience are gamers. I don't want to oversell us and say it's the web, but it's an interesting stat, and we're going to try to dive into that some more, but it does seem to highlight some opportunity. Web gamers are simply gamers. I mean, the genres, the things they want to play, the demographics, very similar to what you know. Browser games, very popular. You saw a couple of opportunities to explore in the core genres. And web games are also social. There's all sorts of interesting acquisition and engagement opportunities. We like to think of it as the power of the link. ways to kind of virally bring people into the game, connect, maybe acquire users in a less expensive way. So thank you. That's it for this. When you leave, we do have Sandra in back, and we have some T-shirts. I happen to be wearing one. Looks just like that. We would love for you to grab it. Little interesting tidbit, the agency we worked with actually did a 3D model in Unity of a room with a little fox sitting there, and then we took it off and modeled it and flattened it out to make the shirt. So there is actually a 3D fox out there, and one day we might do some Lego, hopefully if Sandra lets me. So that's it. Let me hand over to Jonas here. Thank you.
Thank you, Andre. I'm now going to talk to you about the WebGL export in Unity 5. So WebGL, we shipped WebGL support as a new build target in Unity 5.0. It is labeled as a preview because it's there, you can use it, it works, but we don't believe that currently the experience across all browsers is solid and consistent enough to consider it a fully supported product. As I said on the roadmap today, I cannot give you a timeline for when we will drop the preview label because that is kind of dependent on too many external factors of technologies evolving in the space. You'll hear more about that later. Maybe first some clarification. When we say WebGL, that's actually a bit of a misnomer. So what we really mean is the complete technology stack of using WebGL for rendering, using web audio for sound, the JavaScript language. So the whole technology stack provided by the browser to give a native browser experience, as opposed to like using a plugin like the Unity web player. So how's this possible? How do we get Unity content into the browser? So we use the mscripten compiler, which is built by Mozilla, which is a compiler which cross-compiles C++ code, like the Unity source code is mostly C++. So we cross-compile that into JavaScript code using mscripten. Then we use IL2CPP, which is our new scripting runtime, which is also capable of cross-compiling into C++. It takes your .NET bytecode, which is generated from your C# or Unity script sources, and cross-compiles that to C++. So then we can also take that to JavaScript using mscripten. One thing which is important to understand is that WebGL as a platform, it's not a drop-in replacement for the Unity web player. This is something a lot of people are asking about because ever since Chrome announced dropping support for browser plugins, people are looking at replacement. WebGL is our new technology for putting Unity content on the web and will be, at some point in the future, the only technology for bringing Unity content to the web. But it's also fundamentally a different platform than the web player is, and it has different constraints. So I'll talk more about that. But it does give you one huge advantage over using a plugin like the web player, which is that it takes away the barrier of a plugin install, which gives you a much wider reach and potential audience. So I mentioned limitations and constraints. Let's look at what those are. There are some features in Unity which are not yet supported in WebGL. That is the Substance procedural texture rendering system. That's the real-time global illumination using Enlighten. That's the movie texture class for playing back video in your content, though I will show you a nice other way how you can do that later. All of these are theoretically possible in WebGL. We simply haven't gotten around to porting them over yet. But then there's also some features which are not yet possible by the platforms due to platform constraints, but which we expect to be possible in the future. Most importantly, threads, as JavaScript does not yet have a notion of threads which really translates to our use case. That will change in the future with the shared array buffer spec, where Luke I will talk a bit more about, I think. Audio is a bit limited in WebGL right now. You have audio works, but you have basic 3D positional audio and not much beyond that. That's because we use a different implementation for audio than we use on other platforms. On other platforms, we use the fmod library, but that relies heavily on threads, so we can't use that. So we have a custom audio backend for WebGL based on the Web Audio API. Likewise, debugging is not really supported yet. We have some ideas on how to solve that in the future as well. Then there's some functionality which doesn't really map to the platform and doesn't work now and probably also will never work in the future. Most importantly, that's IP sockets. So if you're using the system.net namespace for networking, you won't be able to use that in WebGL because browsers don't really expose direct access to sockets to JavaScript for security concerns. It is possible to do networking using WebSockets, using WebRTC. Our new multiplayer library that uses WebSockets when you build to WebGL, so it's possible to use that. Also, since this platform is using IL2CPP, which is a ahead-of-time compiler, any JIT features in the .NET runtime, like where you dynamically emit code at runtime, are not supported. But this is no different from other AOT platforms which we had before, like iOS, like consoles. But it's different than, for instance, the web player, where you could use code like that. Some other constraints are performance. Due to us cross-compiling everything into JavaScript, there's a gap between native performance and what you can expect in WebGL. This gap is becoming smaller and smaller ever. There's more on that later. And another concern is scalability. One thing is that you have to set up your project to be downloaded, so you don't want to have a several hundred megabyte upfront download before the project starts, because everybody would have closed the page at that point. So you have to design your content around that. But another scalability concern, also concerning project size, is memory. And Marco will tell you more about how memory is used in our WebGL exporter and how to avoid the constraints later. Before we get to that, I'd like to show you some unique things you can do when you target WebGL. So I'll show you how to embed JavaScript code into your project, so you can use HTML5 features directly from your scripts, and how you can interact with browser features. So here's a sample of a JSLib file. We use the JSLib extension. Now you can see it better. We use the JSLib extension to denote JavaScript code, which will then be merged into the build output by Unscripten. Unfortunately, the .js extension is already used for our Unity script language, so we couldn't use that. So we use JSLib. If you put a file with the JSLib extension into your assets folder, the file will be merged into the build output, into the final JavaScript. So in this example, I didn't want to do that. We have a line down here, merge into, which tells the Unscripten compiler to merge this into the build output. And we declare one single function, hello alert. It takes a string parameter which is passed from native code. We call a utility function pointer stringify to turn that into a JavaScript string, and we call the JavaScript alert function to display that string on the screen. Then we have a C# mono behavior file where we call this function. So we declare the function hello alert as a static extern void with the DLL import internal attribute, which tells the compiler that this function comes from the code but outside of the C# or of the .NET generated code. So then we can call this function and pass in a string, as we do here. And when we run this, just put these two files in a project, add the mono behavior to scene, you get a JavaScript alert in your build. That's not very impressive. So let's look at other things you can use this for. Here, again, we have a JSLib file. This one declares two functions, WebGL movie texture create, which takes a URL. So then it generates a video element on the web page, sets that to be invisible, sets the URL as its source, and plays the video. And then it puts it into an array of video elements and returns the index so we can reference it later. Then we have a function called WebGL movie texture update, where we pass in that video reference and the texture reference. We use the WebGL APIs to bind the texture, and then we call the text image to D function on WebGL, which can take a video element from HTML as a source parameter, which will then upload the contents of the video to that texture. So here's a simple mono behavior which uses this. Again, we declare those two functions as DLL import internals, so we can call them from C#. We call the WebGL movie texture create function and pass in a local path to from in the streaming assets folder, which will be copied to the build output as the URL. Then we create a texture. We create a primitive cube game object. We create a material on that game object and set the texture on the material. So now we have a cube with a texture on it. And in the update function, we call the WebGL movie texture update function, pass in the instance of the WebGL movie texture we created, pass in the texture ID of the texture which we created, and this will upload the content of the playing video into the texture every frame. So then we rotate the cube, and then, well, this is a static slide, so you don't see this, but you would see video playing on a spinning cube in the browser. So this is only really a few lines of code you would need to build a video playback solution which you can use in WebGL, and which is actually you can do more than Unity is built in movie texture, because you can use all the video formats available by the browser. You can do video streaming, you can seek in video, and all of those are easy to expose like this. In fact, you don't even have to write that code, because I did, and I uploaded it to the asset store, so you can get a package to do that. There's a few more packages like this. I made a small wrapper which lets you use WebSockets for networking. And so this is a nice example, but you can easily use this mechanism to easily integrate any of the web APIs and to interact with the web page around you. And to be like, to have content which actually behaves as a proper web page. So now my colleague Marco will tell you about memory constraints and performance when using the Unity WebGL export.
Thanks, Jonas. Hello, everyone. I'm Marco. I'm a software developer at Unity, and I work in the WebGL team. Today I'm here to talk about memory constraints and performance in Unity WebGL. So memory. We have seen some people experiencing memory-related issues, and especially when porting existing content to WebGL. And even at Unite, some people came to us and asked, why am I getting this problem? I have this error, I don't know what's going on, what I need to do. And we'll get to the errors later, but first I'd like to explain how memory is used in Unity WebGL, so that you understand why and what to do. So we need memory for the Unity heap. which is the memory where all the native and managed objects of your current scenes are stored in memory. And basically, the Unity heap is just an array of bytes in JavaScript, which will need to be allocated by the browser. Now, the problem is if this buffer is too large, then the browser will fail to allocate. So that's important to keep it as small as possible. And you can change the size of the Unity heap in the player settings. In publishing settings section, there's a WebGL memory size. By default, I think it's set to 256, but it can be larger or smaller. So keep it as low as possible, and you can inspect the content of the Unity heap using the memory profiler. It works like on any other platform, so that you can you know where the memory is going, and you can optimize. And then we have we need memory for data. So on WebGL, there's no file system, and the data for your build will need to be downloaded entirely and kept in memory. If you look at the deployed build of a WebGL target, there's going to be a .data file that contains all your assets and scenes of your build. That will be downloaded in a compressed form if the server is configured correctly, otherwise uncompressed. But it will be stored in memory totally uncompressed. And that's why it's really important to optimize your build size. And you can use the common Unity best practices to optimize your build. Also, on WebGL, you can use a texture compression called Crunch, which gives you similar compression ratio and quality to JPEG. But unlike JPEG, it will decompress directly into DXT, which will save memory. And also, our recommendation is to make use of asset bundles so that you can ship a build that is really small to get your content loaded, and then load all the rest of the assets using asset bundles. That will give you better control on when the memory is used. And basically, you need an asset, then you load it using the asset bundle system, and then you dispose it. And the memory will be deallocated. That's a fundamental difference compared to having the assets shipped in your data file. Also, I should mention that we are working on getting LZ4 compression for your data. So that will also help to save memory. And then we need memory for your code. So on WebGL, your code is basically a huge JavaScript file, and if you load it in a text editor, it will take some time to load and to render on screen, because that can be quite large, especially if you're using a development build. It can be quite big, and it's not the usual use case for browsers as well. So that can take a lot of memory, and there's something that is being worked on, which is WebAssembly, which Luke will talk about later, which is going to make this problem less relevant. But in the meantime, it's important that you keep the size of your code as small as possible. There's a few things you can do. First, you can Make sure you enable stripping, again in the player settings, and disable exceptions unless you need them, and which, by the way, by disabling exception, you're making your code smaller and also faster. Also, be aware that third-party libraries, third-party plugins can reference code from MS-Core, lib, or .NET, and can pull a lot of code and increase the size of your JavaScript code. So now that I explained how memory is used, let's look at those errors. And so when there's a memory error, we try to parse the error from the browser and give you a human-readable message. In this case, auto memory, if you are the developer of this content, try allocating more memory to your WebGL build in the WebGL player settings. Your content is running out of memory in the Unity heap. This is Unity unable to allocate something out of the Unity heap that is allocated by the browser. So there's two ways to solve this problem. Either you increase the size of the Unity heap in the player settings, like we have seen before, or you optimize your content using the profiler. On the other hand, in this case, the browser is running out of memory. The browser could not allocate enough memory for the WebGL content. If you are the developer of this content, try allocating less memory. So, in this case, the browser is unable to allocate memory for either your data or the Unity heap. And the way to solve this is just to use less memory. So reduce the size of your data or reduce the size of your code or reduce the size of the Unity heap. In this case, increasing the size of the Unity heap will not help, will actually make the problem worse. So it's really important to understand this. And or in other cases, you get Chrome crashing, which is very unfortunate. And it doesn't say much about what happened, and can be a lot of different reasons. But if it occurs when loading the WebGL content, loading the page, it likely means Chrome ran out of memory. If you look at the process memory usage of Chrome, you'll see a spike loading the WebGL content, and that occurs when parsing the JavaScript code. Now, this problem will probably go completely away once we have WebAssembly. In the time being, on your side, you can try to reduce your code, and hopefully Google will fix it. Actually, they just submitted some changes to the latest Chrome Canary build. So if you run into this issue, you should check it out with the latest Canary build and see if your problem is fixed. In terms of performance, so on WebGL, you can use the Unity profiler to see how your content performs. But it's really important to understand what to expect from Unity WebGL. And for this reason, we built some benchmarks, which is basically a collection of Unity scenes that stress different parts of the engine, like, for example, physics or 2D rendering on CPU and GPU, and so on. What we found is that in certain areas, WebGL is slower compared to native code, and that's kind of expected. But in some areas is like, for example, in areas like physics that relies on threads, skinning that is in the engine is implemented with heavily optimized SIMD code. Those are areas where the performance gap is bigger, and the reason is that those SIMD and threads are not available yet. They are being worked on, and again, Luke will talk about those. So things will improve and get better, but it's important to know that. And then we found that in other areas, like, for example, on GPU, there's barely any difference. And actually, why would there be any difference? Because the graphics card is the same, the drivers are the same. So if your content is GPU bound, there shouldn't be any difference in terms of performance compared to native when you run in WebGL. And then in other areas, like, for example, scripts, we found that actually on WebGL, it turns out it's faster. And that's because WebGL is a ahead-of-time compiled platform. And our IL2CPP compiler can perform some optimizations that lead to better performance. And we also noticed that there's difference in performance between different browsers. And that depends on the browser on which ASM.js optimizations are implemented. But if you want to know more about the benchmarks and performance, if you want to see how the browser perform in those different areas, we published a blog post. So if you Google WebGL Unity benchmarks, you can find the link to the blog post, and you can run the benchmark on your machine as well. And now I'll hand it over to Luke, who's going to talk about the future of the web technology platform.
Thank you, Marco. Hello, everyone. My name is Luke Wagner. I've been an engineer at Mozilla for the last 6 years, mostly working on JavaScript engine optimizations, ASM.js, and now WebAssembly. So today I'm going to be talking about some exciting new web technologies that are coming down the pipes, specifically in the areas of CPU performance, memory, and graphics. So in the area of CPU performance, basically JavaScript is our abstract CPU of the web today. So let's talk about the performance of compiled JS. So for historical context, I took a simple C benchmark and I compiled it to JS using mscripten, which is the same tool used by Unity. And I ran this same JS on 10 years of Firefox and going all the way back to Firefox 2. So I'm going to point out that the y-axis is a log scale. So what we're seeing here is actually a 388x performance increase over the last 10 years, going from 600 times slower than native to currently about 1.55x. Depending on the workload, of course. Another thing to point out is that there's no one big drop. This has been continual incremental improvements as JavaScript engines evolve from simple interpreters to fancier interpreters to simple JIT or just-in-time compilers to fancier JIT compilers, and then they grew beefy backends that start to resemble C compiler backends, and finally the advanced ASM.js optimizations. So what drives this? Well, two things. One is browser competition. So we currently have 4 big benchmarks made by Unity, Apple, Google, and Mozilla that all include ASM.js. And this naturally, just competition forces everyone to optimize ASM.js. But another equally important feedback cycle goes between browser vendors and cutting-edge developers like Unity who try out all the new things that browser vendors are making. So the sequence goes, browser vendors add some new feature or new level of performance. Cutting-edge users use that, push it to the max, show exciting new things, and hit new limits and feed that back to the browser developers who are like, wow, you have use cases. Cool, let's optimize and push this further. And it goes around and around and moves the web platform forward. So I want to talk now about some of the challenges, the current set of challenges that we're looking at and the fixes that we have coming down the pipes. So one that was already mentioned by Marco is that currently JavaScript, when uncompressed, is really quite big, a lot bigger than native code. Now, fortunately, it compresses really well, and after gzip compression, it's about the same size as native. And so over the wire, it can be the same size as native, but this requires server-side configuration, which not all developers can do or know that they need to do. So our fix here is to do the compression in JavaScript. As we were just talking about, JavaScript's pretty fast now. But as an additional advantage, when you do the compression in JavaScript, you can use more advanced forms of compression, like more aggressive generic compression algorithms like LZMA or LZHAM, or even JavaScript-specific optimizations. And we have prototypes here showing 20 to 40% size reductions over the wire beyond what you can currently do with gzipped JavaScript. So that's pretty exciting. Another area is unlocking all the latent parallelism that's in current hardware. So this is both multiple cores and SIMD units. So we've been working on this for over a year, and we have two big proposals currently we're trying to standardize in JavaScript. The first one adds the missing link to compiling multi-threaded C++ to JavaScript. Currently, the web has workers, and roughly a worker is like an OS thread. But each worker lives in its own universe, so it can't share memory, which is important for shared memory C++. So what shared array buffer gives is the ability to share specific arrays of bytes, which mscripting uses to model C++ heap between workers, as well as the atomic primitives and blocking mechanisms based on futexes, such that you can implement all your own locking primitives like mutexes and condition variables. And so this proposal has support from multiple browser vendors, and we're currently, actually today or yesterday or tomorrow, presenting in TC39 and feeling good about it. The other proposal is SIMD.js, and the basic idea here is exposing fixed width vector types, like an array or a vector of 4 int32s, and operations on these vector types that map directly to the SIMD hardware on the devices. So the other two issues, load time and browser variation, are harder to fix within JS. In the case of load time, after you've removed all the other sources of load time overhead, the JS parser itself becomes the major bottleneck. For example, on mobile, just parsing all the Unity source, not even compiling it, takes about 20 seconds on the Nexus that I was testing. And for the case of browser variation, as we already mentioned, because JavaScript is a high-level language, there's a lot of different ways to compile it, and not all the browsers have used the same compilation strategy that Firefox and Edge, and now Edge, have used. So to address both of these issues, for almost a year now, we've been working with all the other browser vendors on a new standard called WebAssembly. And the basic idea of WebAssembly is you take ASM.js and you take out all the parts that are inherited from JS that we don't want, that are reduce performance or add complexity. Of course, we keep all the important things like safety. And then you replace the human editable text format with a binary format that's performance friendly. And simple prototypes so far have shown we can expect more than 20x performance improvements decoding a binary format compared to decoding the equivalent JavaScript source, or parsing the equivalent JavaScript source. And unlike most big features which have a chicken-egg problem, where browsers don't want to implement until there's a bunch of use cases and users don't want to use until there's browser support, we already have tons of use cases with ASM.js. Tons of users just asking for this feature. So this and a lot of other reasons have really pushed browsers to be really interested in this. And so I'm happy to say we currently have very active participation from 4 browsers. In particular, both Apple and Google engineers are landing code preparing for WebAssembly in their relative experimental repos. Which is great. Also, because WebAssembly is based on the same tight integration strategy with the web as ASM.js, there's going to be a particularly smooth transition path for current users of Mscript and Unity from ASM.js to WebAssembly. In particular, when WebAssembly is supported in browsers, it'll just be as easy as flipping a flag, and then instead of emitting JavaScript chars, we'll emit WebAssembly bytes, and things will just keep working except go faster. Also, because it's similar in spirit to ASM.js, even before browsers have native support for WebAssembly, in the client we can translate the WebAssembly into ASM.js and run it as JavaScript. So it can run on browsers today, and we have prototypes showing Unity running with a pseudo WebAssembly bytecode using client-side translation to ASM.js. And it actually is a size reduction, so it's actually possibly a win even as is. Right. So that's just a really high-level bits of information about WebAssembly. There's a lot more about the design, and you can participate in discussion at the GitHub repo. So that's C performance. We're also looking at some challenges in memory. So one that we've already talked about is that because the main thread of the browser doesn't have access to synchronous file I/O, we have to store all the assets in memory, which of course can be a big problem on like 32-bit when you have a lot of assets. So a short-term mitigation that is landing now is shrinking that size in memory by using LZ4 or some other efficient compression to compress the assets in memory. But the long-term solution, or not even, or medium-term solution we're working on is just to be able to run the games in workers. That means putting things like WebGL in workers, which is happening now in Firefox and soon Chrome. And then, the assets can go in files just like they're supposed to. Another problem, already mentioned earlier, is that this heap is a fixed size. So you have to play this game of asking for enough, but not too much. So a short-term mitigation is ASM.js has been extended to allow copying a heap to a bigger heap and then swapping them, effectively having a resize. But the actual good solution is that WebAssembly will simply have a resizable heap. And lastly, a problem is even though most Windows installations are 64-bit, a lot of the browsers are 32-bit, which significantly reduces the virtual address space. But the good news, and traditionally browsers have been held up by 32-bit plugins, but we're finally moving past that. And so either now or within the next year, all the three main browsers on Windows will be shipping 64-bit browsers. So we'll be seeing a lot more 64-bit browsers in the next year. Getting to graphics, the big feature here is WebGL 2, which adds the features of OpenGL ES 3.0 to the web. And we've been working hard on this and have a good amount of support already in Firefox behind a pref. We can run OpenGL ES 3.0 content exported by Unity, like this teleporter demo. When we are feature complete and stable, we'll enable it nightly, and the goal is to do that by the end of the year, and then ship it on the release channel in the middle of next year. Quickly following after WebGL 2, we want a next version which adds the features of OpenGL ES 3.1, in particular compute shaders. Good stuff. This is just a quick sampling of the major areas that we're working on, but there's a whole lot more on the platform roadmap that I encourage you to check out, such as streaming tiered compilation of ASM.js and WebAssembly, improvements to browser storage and support for offline, and more games-focused developer tools. If you want to find more information about the Games project Mozilla, check out games.mozilla.org. If you have any questions, feel free to email games@mozilla.com. Thank you for all your attention. I'll remind you that we have Firefox game shirts in the back. And I think we have, about 13 minutes for question and answers.
So I think there's 2 mics up here. So if you want to ask any questions, just walk up to them. Also, I've been asked to remind you once again that if you want to go to the party tonight, you should bring your badges and a photo ID, otherwise you won't get in.
Hi there. Right now, the Unity build for WebGL gets a huge JS file with the Unity engine and our scripts. Okay, that means that any single change that I do in the program, that my users need to re-download everything, and Unity's code didn't change. Any plans to separate that?
Yes and no. So we do plan to separate those for development builds, but for a different purpose than what you're asking for. We would like to separate them for development builds to allow you to iterate on your builds much faster, because then we'd only have to rebuild your code every time, and then the build times would go down significantly. For the use case you're talking about, there's a problem with that, which is that for shipping titles, we want to do stripping to avoid shipping more code than you have to, but the stripping is done at a very fine granularity, so the parts of the Unity engine code which are actually remain in the code are very different depending on what your code is. So it's actually not true that the Unity code would always stay the same when your code changes. It doesn't. It will look at your code and strip parts from the engine individually. Also, like we have weekly patch releases, and each one of those would have a different Unity engine build.
Okay, thank you.
When you're showing the JSLib example, where's the documentation for like the merge into and like pointer, like converting from native strings to, is that like an mscriptin like function for compatibility, or like is that on?
Those do come from mscriptin. Okay. We have some documentation on that in our manual for WebGL, where those items you've been asking about are there. I think there's probably more on the mscriptin manuals if you want more details for doing other things. Okay. But at least the basic use cases for passing back and forth basic data types, arrays, textures, and all that, that is described on our manual.
Okay, thanks.
Is there any support for the gamepad API?
Yes. So the input API in Unity should detect the gamepad API of the browser and represent that the same way it does joysticks. It represents joysticks on other platforms.
Thanks.
I'm sure you're tired of answering web player problems, but I've heard rumblings that Firefox is also going to unsupport plugins.
I guess that's a question for you.
Yeah.
Is that going to happen anytime soon?
Yes, and the exact date is TBD. We're trying to figure out the details, but we're trying to figure out the sunset strategy there. I would say that we're also trying to coordinate with Unity. You know, we're trying to figure out a story for the web at large. Don't really have a date to share, but I would definitely keep an eye on the overall WebGL stack within Unity as kind of the future, and probably going to be hearing more in a few months.
Okay. Thank you.
I have a question for the Mozilla guys. You mentioned 64-bit browsers coming. So for us, we've had pretty good success with WebGL, but you know, obviously sometimes we run into the 32-bit issue. Chrome right now has like 64-bit, but they don't push it. Like by default, you know, they point you to 32-bit, right, and they don't obviously auto-update. So it's, you know, WebGL works great on 64-bit Chrome, but no one has it. So right. I'm wondering, do you guys have, when you guys do roll out your 64-bit, do you plan to push users towards it, or is it going to be more like Chrome where it's like,
I think my Chrome auto-updated to 64-bit on my Mac. But maybe that's maybe they have a different strategy on Mac, right, and Windows. But,
yeah, Windows it still points to 32-bit. Okay. So you know, it's great when you know it's 64-bit. But I was just wondering, what are the plans there?
Yeah, so I think the plans are to start by just offering it to all new downloads. So just everyone downloading Firefox for the first time would get the 64-bit, and then after some time and experience and probably some telemetry on how many 32-bit plugins are still out in the wild that would break if we auto-upgraded people, then start, and you know, suggesting to users who don't have any 32-bit plugins that they upgrade. So I'm not sure the exact strategy, but I think it's going to be incremental like that. And I think Chrome was holding back before, also due to 32-bit plugins and other concerns, but they're also going to be more aggressive about actively pushing 64-bit out. I think Edge now is just straight up shipping 64-bit on Windows 10, just by default.
Thank you.
Hey, I have two kind of random questions about bringing our game to HTML5. We had it in Flash previously. And we have basically two problems that are stopping us. One is that fonts are blurry, especially on Retina displays. I don't know if you guys are aware of that, and if it's fixed already, maybe. And the other is, what do you recommend to do with audio if, like, it seems like you have to remove audio and have a custom build for Internet Explorer, or it just won't run?
So for the font question, I have no idea, but if you have it with you, find us at the Ask the Expert table, and we'll take a look together. For audio, the problem is that Internet Explorer lacks the Web Audio API. I think if Web Audio is not there, we show a warning message, but it shouldn't prevent you from running, I believe. So they fixed that and added Web Audio support in Edge. So on Windows 10, you'll be fine.
Okay, cool. Thank you. Question earlier, you mentioned to be wary of plugins. I happen to be developing a plugin, a native plugin. So do you have any guidelines available for native plugin developers?
So when you say native plugin,
It's a C++ plugin that we use.
okay. I think that was not what Marco was referring to. I think he was referring more to C# libraries, which would drag in like big dependencies from MS core lib, like system.xml or so, which then drag in half of MS core lib and add a lot of managed code. So I mean, for native plugins, so in our WebGL export, it's actually possible to drag C++ files straight into your assets folder, and because we compile everything through C++ through Emscripten, they will just be dragged in along with the compiler and be also compiled with Emscripten. I mean, I guess whether you can use that or not depends on why you're using C++, because typically when people write C++ native plugins, the use case is to interact with low-level OS APIs, and of course you don't have those in the browser. But maybe that question is too specific for the audience, and we should discuss it later at the table downstairs.
All right, no problem.
Thank you.
Well, do you see a future where you can have the ability to either chunk what you're sending out as WebGL or streaming it through Unity, so the user is only getting maybe the first level instead of not the entire package?
Yes, so the generic way of doing that on not only WebGL but any Unity platform is that you split up your content into asset bundles.
Right.
If you have a setup which is very linear, then like our web player, it had this option of building a streaming web player where it would start downloading the first level and it... Are we out of time? Or? Where it would download the first level and then you could start playing that while it downloads the next ones.
Okay.
I built a plugin on the asset store which should do the same thing for WebGL by like patching the build a little. So you can try that.
Perfect. That can be cached, like through IndexedDB or something?
We support caching in IndexedDB, yes.
Awesome.
Yeah.
Thanks.
This is more of a Firefox question, but so you're making JavaScript run faster every day, right? But Google keeps on pushing Dart, and I think from the start they said, even if you compile Dart into JavaScript, it runs like 20% faster. So I guess what I'm saying is Mozilla ever going to drop, do you think JavaScript is ever going to be like obsolete when people stop using it, or do you think that people are going to stop using it for Dart, or like what's the plan?
Well, the Dart part's easy. Google's publicly announced that they're discontinuing the Dart VM, and it's not ever going to merge into the Chromium source code. So they've kind of reoriented the Dart team to more be like, I think, more like TypeScript, be more like a developer-side productivity tool that gives you type checking, and then like TypeScript, it erases to JavaScript. So Dart's future in the browser, it's not going to be a language that you ship. As for JavaScript, it has, I think, an unfathomable amount of momentum behind it. So I don't see it going, anywhere in the conceivable, as far as ahead as one can predict without taking into account apocalypses. So, yeah, even with WebAssembly, I see them being very complementary. A lot of the design of WebAssembly is to let JavaScript be what it was designed for, which is a scripting language with dynamic typing that lets you glue stuff together. What I anticipate, and what we're already seeing with ASM.js, is people making compiled components of things like physics engines or audio engines or graphics libraries or all these things, and then you wrap that in a nice little JS shell. And with WebAssembly and the integration with modules, even that shell won't be so much necessary. And then you just use those components from normal JavaScript, which gives you a lot of power, and that's what JavaScript was designed to do. So I do see JavaScript, staying around for a very long time.
Okay. Thank you.
Hi. Most of the content is consumed on iOS or Android phones and tablets, basically. Unity can export to these platforms directly. What is the benefit of exporting to Firefox or Chrome or whatever it is to run on the same platform as another layer?
So you mean what would be the benefit of using WebGL to target mobiles?
Basically, if you run on an Android tablet or iOS tablet in Firefox, why just not do it directly from Unity?
So at this point, if you want to target Android or iOS, I very much recommend that you target them natively. because I think we very much care about the use case of having WebGL on mobiles in the future, but right now we find that it just doesn't really scale to what people want to do on those phones. Some high-end phones can do it, but for the majority of them, Unity content is not really yet an option to run on WebGL. So I agree with you. For those platforms, I would use the native export options for feasibility. But looking into the future, where I very much hope and expect that using WebGL to target mobile will be an option, I think there's a few reasons to do it. It could be that you want a more web-integrated offering than an app, like that you want a web page people surf to, which has like 3D interactive content, that you want your content to be reachable by just clicking on a link and all that. So I think all of that makes a lot of sense to use WebGL. I also know that for another reason people are interested in this, because there are some people who just cannot go through the app stores because they want to do content which doesn't comply with the guidelines of the app stores, for instance. So I think there's plenty of reasons why people want to target mobile devices with WebGL. But at this point, with the state of technology, I don't recommend doing that using Unity, because it's not quite there yet. But I'm pretty sure it will be in the future.
Thank you.
So I think we're officially out of time. I don't know, like, how urgent we need to get out of here.
Very non-technical question. Very simple for Andre. Is there any way we can access the data you talked about at the beginning? I can really use that as background in my research.
Great question. The answer is probably. I mean, obviously it's been videoed, and the video is going to be out there somewhere, and you can get it. What do you mean by access?
I just need.
I mean, all these talks will be online as video.
Okay, but the data itself, you can't give it to anybody?
No, well, the charts we can share. The data, I mean, we're very careful with user data in general, and as it was, just collecting the data and anonymizing it and making sure we're doing the right thing. It took some effort, so actually sharing the raw data just doesn't happen.
All right, thank you very much.
Yeah.
Okay, guess that's it then. Thank you for listening. Thank you.